Hello, this is Mr. P, and today we're going to learn about absolute value inequalities. And we're going to first take an analytical approach to solve these, and then we're going to look at a more geometric approach. Analytically, we have a pretty good rule set up for handling absolute value inequalities. If you have the absolute value of an expression is less than a number, then that's going to be the equivalent of saying that that expression is going to be between the positive and negative versions of that number. So it would be between negative c and positive c. And if you have the absolute value of an expression is greater than a number, then that means that the expression is either less than the negative of that number or greater than the positive version of that number. So, and these rules are going to be the same whether there's an or equal to or no or equal to. Now, when we solve the equations, and this is going to be our example here, when we solve an absolute value inequality, generally you would break it up into two cases and work the cases separately. But before we can do that, we have to isolate the absolute value. So our first step is really to isolate the absolute value. So we're going to subtract 1 from both sides, and that will give us this. And then we don't want 3 times the absolute value, we want just the absolute value. So we're going to divide both sides by 3, which would give us this line. Now once we have it down to absolute value, and then inequality, and then number, now we're ready to break it up into our cases. And let's look at how we do that. Alright, so here we would have two cases. We're going to break this up into two different cases. The first case would be what we call as is. In other words, we take this and just ignore the absolute value. So this would just be x minus 4 less than 3. And then the second case we refer to as negate the outside, because everything inside stays the same, but we take the negative of everything outside the absolute value sign. So x minus 4 is inside the absolute value, so that stays the same. But then the negative of, and that includes the inequality symbol, the negative of the less than would be greater than, and the negative 3 is negative 3. Make sure you switch your sign when you're taking the negative of the outside. Switch the direction, of the symbol. Now, in mathematics, whenever we break something up into two cases, you do have to have a logical connector. And the word will be and, or the word will be or. And which one depends upon this symbol, which is the one from just before when you break it up, whether it's greater than or less than. And a good mnemonic, a good easy way to remember it, is you can think of less than or great or. So if this symbol is a less than symbol, like it is, then the word between them will be and. If this was a greater symbol, then this would be or. Now once you have it broken up, you can solve each side individually. Here we're going to add 4 to both sides, which gives us x is less than 7. And that follows along with us. We add 4 again to both sides and get x is greater than 1. And sometimes when you have an and statement, you can rewrite this as an interval. We basically rewrite it as an inequality of 1 is less than x, which is less than 7. 1 would be your lower bound, 7 would be upper bound, and x is between 1 and 7. And then if we were to graph this, we would have our number line with the critical points 1 and 7. And we want all the values between 1 and 7, not including the endpoints. So this is what our graph would look like. We shade in the values in between, and we use brackets to show, parentheses, to show that we are not including the endpoints. We do not include the upper and lower bounds. Alright, so that's the way most people are taught to solve an absolute value inequality. But sometimes you can do these a lot easier and quicker if you have a little bit of understanding of what these really mean. First of all, absolute value means distance. Absolute value means distance. And if you think about the absolute value of a number, is its distance from 0 on a number line. And even a complex number, is going to be the absolute value of a complex number will be its distance from 0 on a complex plane. That's something we're going to see in later lectures. But absolute value means distance. That's the key here. So when we get to this line, you're still going to have to isolate your absolute value. When we get to this line, we have an absolute value inequality. And geometrically, I want you to realize that absolute value inequalities are intervals. We can see the result of working this problem. We got an interval. That's because absolute value inequalities are intervals. So an interval is going to have two important things. It's going to have a center, and it's going to have some distance from that center to the endpoints, or to the bounds. The center is pretty easy to figure out because it's simply the value of x that causes the inside of the absolute value to be 0. So the center is the value of x that causes the inside to be 0. And if we look at this case, we have x minus 4, and think of it as x minus 4 equals 0. Well, if x is 4, then that would be true. So the value of x that causes the inside to be 0 is 4. So that will be our center. And the distance is simply the number on the outside. Once you've isolated the absolute value, it's going to be the number on the outside unless there's a coefficient. If there's some coefficient of x, then you would divide by that coefficient. So we can say it's the outside number divided by any coefficient of x if there is any. So it's 3 divided by, well, 1, because technically 1 would be the coefficient. So 3 divided by 1 is 3. So the distance from the center to the edge would be 3. And those are the only two pieces of information you would need to know in order to be able to go right to the graph. So if we were to graph this, we would have our number line, and our number line centered at 4. And then from 4, I'm going to go 3 units left to give me 1, 3 units to the right to give me 7. And then I want everything that is less than 3 units away from 4. So I want everything near 4. So that's why I shade in what is within 3 units of 4. And don't forget to use the parentheses because we don't include the endpoints. There's no or equal to. And we're done. So if you really understand what these absolute value inequalities really mean, then you can basically look at this and say, well, it's centered at 4 with a distance of 3, so it's 1 and 7 are the endpoints. So you can solve a lot of these in your head. All right, let's look at one more example, though, because sometimes you do have a little more complicated stuff, but one more example. Again, we're going to solve this both ways. So the first way, the analytical way, is we're going to break it up into two cases. First case is as is, which means we just ignore the absolute value inequality. The second case, we're going to negate the outside. So 5 minus 2x, that doesn't change. But then everything outside, the greater than becomes less than. The positive 7 becomes a negative 7. I broke up in two cases, so I need a word between them. And since this symbol is greater, it's going to be great or. Now on the first inequality, we have subtract 5 from both sides to give us this line, divide both sides by a negative 2, and this is where you do have to be careful. Whenever you divide both sides by a negative number, you must reverse the direction of the inequality. So divide both sides by a negative 2 gives you x is less than negative 1, because we have to change the greater than to a less than. And then, of course, we bring down the or. That doesn't change. And for the other case, again, we subtract 5 from both sides, which gives us this line. We once again are dividing both sides by negative. Whenever you multiply or divide by negative, you reverse the inequality. Adding or subtracting does not change it. So we divide through by negative 2, and we get x is greater than 6. So if we think of our number line here, our critical values are negative 1 and positive 6. I want everything less than negative 1. Less than means to the left of. So I'm looking for everything to the left of negative 1. So I have a bracket. I have a parenthesis because there's no or equal to. a parenthesis at -1, I shade in everything to the left, and I draw the arrow because this will be an unbounded interval off to the left. And for the other side, I have everything greater than 6 is to the right of 6 on a number line. Again, I have a parenthesis because I'm not including the endpoint. And then I shade in off to the right with the arrow to show that this goes on forever. All right, so that's the analytical approach. Let's think about the geometric approach. So again, this is an interval. Absolute value inequalities are intervals. The absolute value is already isolated. So I can think about what is the value of x that causes the inside to be 0. That is going to be my center. All I need to figure out is center and distance, and then I can go right to the graph. Now, if you can do it in your head, great. If not, just realize that it's 5 minus 2x equals 0. Solving that equation will find the value of x that causes the inside to be 0. So you subtract 5 from both sides, divide through by -2. X is going to be a positive 5 halves. So the center is 5 halves. And then the distance is simply this number divided by any coefficient. And we can ignore the negative here because we're talking about distance, so we only care about the positive one because we're going to talk about distance left and right. So 7 divided by 2 is 7 halves. I don't care about positive or negative because I'm going left and right of the center anyway. I'm accounting for both cases. So 7 divided by 2 gives me 7 halves as my distance. That means I have a number line centered at 5 halves. And then if I subtract 7 halves, then 5 halves minus 7 halves would be -2 halves. And -2 halves is the same as -1. If I add 7 halves, 5 halves plus 7 halves would be 12 halves, and 12 halves is 6. And since our distance is going to be greater than that, I want everything that's outside of the 7 halves distance. So again, I want everything to the right of and everything to the left of those critical values. And like before, I'm not including the endpoints. That's why I have the parentheses, because there is no or equal to. All right, so we have the analytic approach, we have the geometric approach, and we're done.